Welcome to part 2 of the key moments in the history of quantum mechanics, a series of videos developed for General Chemistry Chem 181H at Michigan State University. The goal of these videos is to understand how did we arrive at our present understanding of atoms and molecules. In this part, we will be covering how electricity, magnetism, and light were unified by Maxwell's equations, that during this time, chemists were already creating their first periodic tables and had derived the concept of valence based on equivalence, not electrons. Boltzmann thermodynamics law implies that gases are made out of atoms or molecules and that these are likely to have discrete energy levels. That atoms are found to emit or absorb light at very precise or discrete wavelengths, and electricity and light are experimentally related, and that the speed of light is found to be constant independent of the direction of the speed of the emitting object. So we're talking about light, okay? And so people were familiar with light. Of course, they could see the sun and so on, but they didn't know what light was. And that gets solved by Maxwell. And he writes these equations that have to do with the electric field and the magnetic field, and how electricity is related to magnetism and magnetism to electricity, okay? And when you solve these equations, you end up with a formula that you have an oscillating field, okay, either magnetic or electric field, that induces another, conversely, if it's an electric field, induces a magnetic field, and so on, that's perpendicular to it, and that travels at the speed of light. And so basically the solution of this equation is an electromagnetic wave traveling at the speed of light, what we know as light, but that needed to be shown, right? You needed to do an experiment that shows that with pure electricity and maybe some magnetism, you create light. That's what's missing. But essentially, this laid out the existence of light traveling at the speed of light. Okay. Now, we've been talking a lot about physics and electrons. What were the chemists doing during that time? Well, you would see that the chemists were very busy. So by 1864, Mayer already classified 28 elements by their valence. And it's interesting because if you've studied some chemistry, we know about valence electrons. So could Mayer understand valence electrons before we even know electrons exist, right? But we knew something about equivalence. And so in those days, valence meant more equivalence rather than a certain number of electrons. And Newlands had a law of octaves, and he had already 56 elements classified. And then in 1969, Mendeleev, which is, by the way, 150 years ago, Mendeleev published his periodic table and predicted a number of new elements. And so all these periodic trends were qualified by these valence, but they did not know about electrons, okay, and their masses. And so here's a picture of Mendeleev's, this is Mayer's periodic table, because I wanted to go to the earliest one, right? So if you see, this is the valence, okay, 4, 3, 2, 1. And then not only that, but here you see there's one kind of like negative, right, fluorine, chlorine, bromine, and one kind of like positive, lithium, sodium, potassium. Really cool. This is 1869. Okay, got it. Okay, so going back to physics, okay, we see Boltzmann's work. And Boltzmann was interested in understanding gases from a microscopic level. Okay, so the laws of gases like PV equals nRT and all that was developed just before that. And he wanted to understand where did all that come from. To understand that, he imagined the gas as being made out of either atoms, individual atoms, or molecules. By the way, he had major discussions with the publishers of journals because they would not accept his description of atoms and molecules. They would tell him that atoms and molecules are figments of his imagination and that there is no proof that atoms or molecules exist. Pretty amazing. But anyway, he kept on this, and so these are kind of like typical thought experiments from a Boltzmann, thinking of, you know, maybe two compartments. One has gas A, one has gas B, and then we open, and how long does it take for them to mix? Things like that, and then predicting laws of pressure, volume, and so on, but from a microscopic level. He wanted to understand, for example, pressure, and, you know, what is the energy of a gas if you compress it, things like that. Yes?
So at this point, were molecules commonly accepted to exist or no?
Oh, well, he believed it, but not entirely. Not entirely, but I would say that Boltzmann laid out the foundation for the existence of molecules, you know, kind of without any doubt. And as just let me say this, as part of his calculations, and he could measure heat capacities and so on. And as he was measuring, he found that if he was working with atoms, he would get a certain curve. But if he would measure things like nitrogen, oxygen that have a strong vibrational component, he would see that there's deviations. And so he proposes, right, working on the gas laws from the point of view of statistics. He was one of the few physicists that believed in the existence of atoms and molecules, and he proposed that the energy levels of those atoms and molecules could be discrete. This is the first time we see this proposal in 1877 of discrete energy levels. Yes?
Historically, do we have protons and neutrons yet?
No. Other than the fact that Franklin, so the question is, do we know about the existence of electrons, protons, and neutrons? What we know is that electricity can be positive or negative due to some very clever experiments from Benjamin Franklin. Okay. There is an equation that Boltzmann used, and this is in his collaborations with Maxwell. So the equation actually comes from Maxwell in 1860, which is quite early. And this is a lot of terms. So I want you to ignore all of these constants. And I just want you to look at the exponential to the minus, and I want you to identify here 1/2 mv squared. Okay? What is 1/2 mv squared? That's kinetic energy. Well, that's the energy of atoms, right? So the kinetic energy of a gas made out of atoms is entirely put together by the kinetic energy of these atoms, 1/2 mv squared, divided by Boltzmann's constant and the temperature. Okay? By the way, this functional form looks very, very similar to the black body radiation curve. Very, very similar. And this formula, we're going to use it later on. You will see where. Okay? So remember, exponential to the minus 1, the energy, 1/2 mv squared over k Boltzmann T. Okay? Well, it'll come back later. Okay. So 1877, proposal energy levels in atoms and molecules by Boltzmann. And we begin to see that in the emission of all these gases where they're running electrical discharges, if you put hydrogen, you get this discrete emission spectrum lines. And if you use white light and you have that cell, you see the absorption lines. Okay? And one of the people that were looking at these lines was Balmer, and Balmer came up with an empirical formula that the wavelength equals bm squared over m squared minus 4. How did he come up with that? Well, by writing a lot of numbers and trying a lot of other things that didn't work. Okay? But And this formula worked for this set of lines. It didn't work for other sets of lines. And it didn't help explain anything about any other atom in the gas phase emitting light. Okay, so now this is a very important experiment. If you remember, Maxwell's equations told us that the existence of light and how an electrical discharge may generate light through some oscillation. And so what Maxwell and so what Hertz came up with is a set of electrodes where he can change the distance between them and the current that he throws through. And then he used a prism. I didn't draw a prism here. To change the color of the light. So this is the emitter. And then he used the secondary spark as the receiver loop, right? And so the idea being that if you generate a light of sufficient energy to dislodge electrons from the surface, that it would jump. Okay, well, he didn't know all that. All he wanted to show was that he can generate light from this discharge and that he could control the color of the light. Okay, so he did that experiment. He looked at different colors, and he found that when he had the UV shining on here, there would be a much stronger receiver spark. He had no idea why. It would take a very smart person to figure it out in 1905. Okay? So that's the photoelectric effect. Now, this is an amazing experiment. Imagine you have an interferometer, but in this case, the interferometer is in motion. Okay? So if the interferometer is in motion, then the particles don't arrive at the same time. But if it's not in motion, they do arrive at the same time. What is this experiment about? This is the Michelson-Morley experiment. And the idea is that if light is a wave, then it must propagate in a medium. Like, imagine propagating in water. So now, imagine that you set this up, but you're in a river. Okay? And so if the river is flowing and you send waves in the direction that the river is flowing, they move way faster. Okay? And so that was the idea. And the medium where light propagates through was known as the ether. So the idea is, let's prove the existence of the ether. And to do this, they did a number of experiments, and they kept refining until they had the absolute stability. And that experiment was very, very cleverly set. Yeah.
So what makes them think the ether is moving? Why couldn't it be still?
Okay, that's a good question. So why should the ether be moving? I mean, we're not moving. But they were very clever. They figured that we see the light from the sun. And so they were thinking big. They said, planet Earth is rotating very fast. Not only that, but planet Earth revolves around the sun in this very large orbit very, very quickly. And so they figured this ether cannot be local. It needs to kind of encompass all this universe. And so they figured that it should make a difference which way this setup is pointing. For example, when we move this way, there's a difference between the blue and the red. If we were moving this way, the difference, the one that is delayed would be the red one, right? And so they figured if we put this on a table and we rotate the table, it should make a difference. Not only that, it should make a difference whether it's the day or the night. Okay? So they made some measurements, and let's see, their apparatus is really amazing. Okay, this is a huge slab of granite, super heavy, that is floating on liquid mercury. And it was set up in the basement, and so there's no vibrations. By the way, they reported being able to see vibrations when there were horses outside. Okay? Yeah, no cars in 1887. And so this was an experimental setup, and the conclusion was amazing. Light always travels at the same speed. Okay? The implications of light travels always at the same speed. So if I have a laser and I shoot light, doesn't matter if I'm running towards or behind, the light is always going to travel at c. And what if I am traveling at the speed of light and I shoot the light forward? Is it actually even going to come out of the laser? And those were the questions that led Einstein to figure out the theory of relativity. Because he took this seriously. He said, wait a minute, these guys did a very careful experiment. Light always travels at the same speed. And therefore, something else must be changing. Maybe space is shrinking. Unthinkable in 1887. Okay? Summary of part 2. We saw that chemists created the first periodic tables, that Boltzmann's laws imply gases are made of discrete atoms or molecules, and that these have discrete energy levels. That atoms are found to emit or absorb light at very precise wavelengths. That electricity and light are theoretically and experimentally related, and that the speed of light is found to be constant, independent of the direction and the speed of the emitting object. In the next part, everything finally makes sense. The first formula that explains the emission of alkali vapors and hydrogen emission lines. We'll see electrons and protons are finally identified, including their charge and their mass difference. That nuclear radiation provides information about the makeup of the nuclei. Planck provides a formula that explains blackbody radiation and implies the existence of photons. Einstein uses the concept of photons to explain the photoelectric effect. Atoms are found to be vacuum except for the very small nucleus containing most of the mass. Lewis dot structures are developed according to the law of octaves. Spin is found to be quantized. Particles are proposed to behave as waves, and the wave nature of electrons is experimentally demonstrated. And by treating particles as waves, quantum mechanics is developed and found to agree with experimental findings.